Hello students, we are going to continue with allotropy, and strictly we are talking about the different allotropes of carbon. Today we are starting with graphite. Briefly, graphite is a black, soft, slippery, solid, and many times it can also be observed as a gray solid. So it all depends on the manufacturer and how it's formed. That is one. Then it has a hexagonal crystalline structure. Hexagonal crystalline structure. If you remember, that's why we say that graphite is a crystalline allotrope. Okay, let me briefly talk about the structure. Now, for graphite, each carbon is bonded to 3 other carbon atoms. Now, if you look at this structure, we have this carbon atom, this carbon atom, this carbon atom. We can have this is a carbon atom, this is a carbon atom, because we can see our key. It shows us the carbon atoms. Then a line represents the covalent bonds. Reason, graphite is made up of carbon atoms, and we said carbon atoms are non-metals or non-metallic atoms. So that means that the different carbon atoms that bond to each other, they do that by sharing electrons. And sharing electrons leads to the formation of covalent bonds. Now, each carbon atom is surrounded by 3 other carbon atoms. 1, 2, 3. So other 3 carbon atoms will pair with the 3 carbon atoms from the central atom. That means that each carbon atom has 1 electron that is free, that is not paired with anything else, like any other electron from the neighboring carbon atoms. So 1 electron is free or delocalized. So this is the electron that is responsible for the ability of graphite to conduct electricity. Because the presence of that 1 electron that is not fixed to anything, or that is not paired to any other electron, it enables graphite to conduct electricity. That's why we say graphite is a good conductor of electricity. Next, these different carbon atoms, they form hexagonal rings. A hexagon is a 6-sided figure. 1, 2, 3, 4, 5, 6. 6-sided figure. So we say that the structure of graphite is a 2-dimensional layered. 2-dimensional layered structure. The reason why I'm saying layered, we have the different hexagonal rings, and these are called hexagonal rings. The different hexagonal rings, they are combined together, or they form layers. We have a layer joined to another layer by van der Waals forces of attraction. These are van der Waals forces of attraction. So van der Waals forces of attraction are very weak. That's why the different layers are not very strongly attached to each other. We say they are slippery. That's why we say these layers can slide over each other because the van der Waals forces of attraction holding the two neighboring layers, or the two layers, they are very weak. That's why, lastly, we say that graphite is soft. You can remember, soft and slippery. Soft and slippery because of the weak van der Waals forces of attraction that are used to combine the two layers together, or that are used to hold the two layers together. Each carbon atom is bonded to the neighboring carbon atom by sharing electrons. And lastly, graphite can be used as a lubricant because of that softiness, or because of the van der Waals force of attraction making it very soft. It can be used as a lubricant. That's one point to note. Another point to note, because graphite has delocalized electrons, as we said, each carbon atom has a delocalized electron, or a free electron. Those electrons are mobile. They are free to move from one point of the structure to the other. And because of that, we say graphite can conduct electricity, or is a good conductor of heat and electricity. Thank you for listening. Next time we'll continue with allotropes of carbon.